Imagine the following scenario. Your friend is going to leave and he's going to drive away in his car, starting at rest, shooting off with some constant acceleration, and eventually reach some distance, some point distance d away, at which point your friend will turn around and return instead with a constant velocity. You're just sitting at home and you don't really record how far away that point is, but you notice the entire trip time. Let's call that entire trip time capital T as 60 seconds, let's say. Now, suppose you know a few things about the car, that you know that it's going to have an acceleration of 1 meter per second squared, and your friend tells you that he drove back at 10 meters per second. So with this sort of setup, knowing how long he was gone for, knowing that the entire trip to go from position 0 to distance d and coming back, can we use this information to figure out how far away your friend was at greatest distance? So to do this, we can't describe it with just one kinematic equation because the change of acceleration between the first phase, where there's a constant non-zero acceleration, and the other phase where there's a constant zero acceleration and the velocity is opposite direction. So we need to describe this with multiple equations. So let's talk about what would be the first phase, the accelerating phase. So we know in this case the initial position is 0 and the initial velocity is 0. The final position is distance d. So if we were to imagine we're going to use the general equation of x equals x naught plus v naught t plus 1/2 a t squared, and also we should have a system of direction, say what the positive direction is, so we'll call to the right positive. With this setup, we can rewrite the equation that the final position is positive d equals initial position 0, initial velocity 0 times time, and we don't know what that time is, so I'll just give it a subscript of a, the time while it's accelerating. And then we have 1/2 the acceleration of positive 1 meters per second squared, and then time squared during acceleration. Okay. So in this equation we have two unknowns, the distance we're solving for and time, which we don't know. So we need more information, but we also need to describe the second phase too. In this case, the initial position of the vehicle is not at position 0, it's starting at position d, and it's ending at position 0, it's returning. So in this case I'd be writing our kinematic equation here a little bit differently. I'd be having 0, the final position, equals d, the initial position, plus the velocity, but in this case, because the velocity is to the left, it's going to be actually negative 10 time, and again, we don't know how long it's going to take, so we need to give this some other sort of subscript. We'll call it time for constant speed, so t sub s, I'll call that. And as for the acceleration, there's no acceleration, that's constantly 0. Constantly 0, t squared s. Alright, so the equation looks somewhat simple, but right now we still have an issue. This equation has two unknowns in it. This equation has two unknowns, but they're not the same unknowns. We don't have enough information yet. But we have one last piece of information. I had told you the total time it took the car to accelerate away and then return. So the third equation I can write is that the total time is equal to the time of the accelerating phase plus the time of the constant speed phase. So we have three equations, three different unknowns. We have enough then to set this up now with some algebra work. So let me just quickly rewrite the equations. Alright, so how might we try to approach a problem like this? Well, in each case, I could, for example, solve for what time is in an equation like this algebraically. So I would have time in terms of d. I could do the same thing with this time here, and I could plug that into this equation. So I could solve for ts here algebraically, plug this in. I could solve for ta here, plug that in algebraically. And then I would have t equals something that's all in terms of distance d, which I'm solving for. So that's the approach I'm going to go through. And so, like I say, this is going to be pretty much a bunch of algebra right now. So the first equation, I can rewrite that if I solve for t sub a. And that's going to be equal to the square root of 2 times the distance. And for the second equation, I can solve for t sub s there. T sub s. And this is going to be just the distance divided by 10. Okay, so I can take that information now and plug it into this equation here. So the total time, which we know to be 60 seconds, as was given before, is equal to square root of 2d plus d over 10. Alright, so if I want to figure this out, I'm probably going to have to square both sides of this equation. And to make sure that when I square both sides I don't have still a common square root stuff, I'm going to move this term over, so I can rewrite this equation as 60 minus d over 10 equal to square root 2d. I can square both sides, and since I'm going to be squaring this entire term, I'm going to actually have to FOIL it out. It's going to be a little bit of fun algebra work. When I do that, I'm going to get, let's make ourselves a little bit of space for this, why don't we? So this is the expression we would get, and I'm now going to bring this term over to this side and just do a slight little bit of rearranging. So I'm going to get 1 over 100 d squared minus 14d plus 3600 equals 0. And I put it into this form so that way you can see now it is a quadratic equation where my variable that I would be solving for is d. So I have one of the constants is 100th, another constant is negative 14, another one is 3600. So I need to plug this now into the quadratic equation. So for review, in case you have not been familiar with the quadratic equation in a while, it's when you have it in this sort of form where d is your variable, so you have some sort of constant in front of the squared term, another constant in front of the linear term, and then some remaining constant that isn't combined with the term you're solving for. When you have that, the quadratic equation, then the solution for d is equal to this form, negative b plus or minus the square root of b squared minus 4ac divided by 2a. And of course, noting that since we have this plus or minus term, we'll get actually 2 different possible solutions for d, and we'll have to pick one of those roots as the one that fits best. So basically now it's plugging everything in and seeing what we get for possible answers for d. When I do that, and I'm trying to be careful, I find that d will have the following 2 possible roots. One is about 339 meters, or 1,060 meters. So then one might beg the question, okay, well, how do I choose either one of these things? Well, consider this. We're ultimately having the problem that the kinematic equations we used are trying to describe the motion of this thing for infinite time, but we're really saying that these are only true for a limited amount of time. So, for example, if all of the time were spent in the accelerating phase, well, how far could your friend possibly have gone? You know, whatever distance that was is further than what he must have done because he has to spend some of that time coming back. So, if we were to reconsider the equation for how far your friend had gone, and let's consider that the case for just when your friend was going constant speed returning. So that distance that was covered, that d prime, the furthest your friend could have gone if he spent the entire time traveling at constant speed would just been your friend's velocity times the entire travel time. Since your friend was going 10 meters per second and the time for the whole thing was 60 seconds, then that would give us 600 meters. So that's if he spent the entire time doing that, but we know he spends less than that much time. So that we know that basically with this sort of setup, d prime has to be greater than the actual distance he's gone. So that's the sort of thought process then we would use to realize, oh, we should be taking the smaller of our two roots. And so this one is the most appropriate. Now, you might not see too many problems like this, but you might think shorthand, okay, the smaller of the two distances is probably the more likely. The other one only happens basically if you're assuming the equations are still correct for the car in plus or minus infinite time, which they're not.